Our notes for today, we're getting into logarithms, the basics of them, and logarithmic functions. First off, let's start out with the basics in terms of the relationships between exponential form and logarithmic form. Exponent or an exponential equation and a logarithmic equation is explaining the exact same relationship between the basics of it, three numbers, but just written in a different order for mathematical purposes. So if we look at exponent form, we have the base of 2, we have the exponent of 3, and then we have the power or the value equal to 8. In logarithm form, it is log, which is simply notation of the word log, and then you put the sub value, just like y sub 2, subscript, that's the base, and then you put what the value is in the exponent form, you put that right there, and then the exponent goes over here. So the relationship of 2, 3, and 8 is the same in both equations, but in the logarithmic form, the exponent is solved for, where in logarithmic form, I think I said that correctly, sorry it's early in the morning, and then in exponent form, what is solved for is the value. Now, like I said over here, this is the base. I'll just put b for base. 3 is the exponent, and then 8 is the value. But we're not going to call it the value in logarithm form because value is associated with output. And for logarithm, that 8 is going to be the input. So over here, our base goes right here. 8, we are going to call the argument. Argument is a synonymous term for input of a function. And that is going to be the input for a logarithmic function. So we're going to call it the argument. Some teachers call it the of, because the way we verbalize is log base 2 of 8 equals 3, and 3 is the exponent. I'll just put an e there. So now for a logarithmic function, our output is the exponent of the relationship of the three numbers. And the input is going to be the whole power, or the value of the power. We're going to call that the argument x. So f of x equals log base a of x. That's how you verbalize it. A always has to be greater than 0, and x is also going to be greater than 0, simply because the value of 2 to some power, or any number some power, cannot get you 0 or less, as we saw in the last section in terms of the horizontal asymptote of an exponential function. Now, a very common base within logarithms, as with exponents, is 10. So we have 10 to the first, 10 to the second, etc. If base a is 10 down here, if we, instead of writing log base 10 of x, we simply write it as log x. It's just a simplification of notation, given the fact that log base 10 comes up often. Okay, just a couple of rewriting in exponent form. You can go ahead and do this individually or just simply watch. Here, this would be 3 to the 4th equals 81. Here, this would be 2 to the 5th equals 32. Other way around, going from exponent to logarithm form, log base 8 of 64 equals 2. Here, the base is the base is 3 1/27. You just kind of write it on line with the logarithm as best as possible, equals the exponent, which is negative 3. Now, when we're plugging into a function, we're saying f of 4. F of 4 equals log base 16 of 4. And the way that I think of it is I say 16 to what power or what exponent will give us 4. Again, 16 to what exponent gives us 4, and that you would square root 16. So square root as an exponent is 1/2. So the output then is 1/2. Here, if we have 10, log 10, remember when no number is written, that means a base of 10. So what we're asking is 10 to what power will give us 10, and that will be 1. So f of 10 equals 1. And now we have a to the negative 3rd equals log base a, and now we plug a to the negative third in, and now we look at this and we say a to what power would give us a to the negative third. And sometimes if it gets a little more challenging, there's no problem with putting it into exponent form. Let's put what we just said in words into equation form. A to what power, a to what power, I could write x if I want, I'm just going to put a blank there. A to what power equals a to the negative 3. And you look at that and say, what would you have to insert into that blank spot or variable spot in order to make both sides equal? Obviously that would be 3. So again, this is function where input is a to the negative third and our output is negative 3. So it's simply doing an input-output table, but the thinking behind it is relatively backwards from what we're used to thinking. Usually we're just, in terms of exponents, we're thinking 4 squared equals 16 rather than the other way. I mean, we do square roots, but in any case it's a little different thinking, but once we get used to it, I think it goes much smoother. So now if we do some evaluations, log 4.5 is saying 10 to what power gives us 4.5, and we can simply use a calculator for that. And what's more important, I think, with these problems is if you look at all three of these, we're looking at log with base of 10. So it's really important, I think, to, well, let's start out with 10 to the 0. 10 to the 0 equals 1, 10 to the first equals 10, because you will be tested on being able to estimate logarithms. So if we look at that, if we have 10 to the 0 equals 1, 10 to the first equals, 10 to the 0 equals 1, 10 to the first equals 10, 10 squared equals 100. And now we're saying here, 10 to what power gives us 4.5, 10 to what power, we want to know the power, equals 4.5. Well, if we look, 1 and 10 is between, 4.5 is between 1 and 10, so therefore log 4.5 is going to be somewhere between 0 and 1. Plug in our calculator, we get about 0.65. Now here, log 86, we look at that and we see that's between 10 and 100, because remember, this is the value or the power, what the total base to exponent equals. It's called the argument again in the logarithm. 86 is closer to 100 than it is to 10, so we're assuming it's going to be closer to 2 than it is to 1. A good estimate would be about 1.8 or so. So if we do plug in our calculator, we get approximately 1.93, and note that seems a lot closer to 2 than 1, and again, this is a logarithm. We'll talk more about the behavior of it, the overall behavior of the function as we move forward, but it's not directly proportional or linear in terms of its growth, so that's why, which we'll see later in the graph, we're not going to explore it relative to this number, but still talk about it, the logarithmic behavior obviously, but it's not directly proportional, and therefore not 86% of the way to 2, so to speak. Okay, so log base 10 of negative 5, or log negative 5, as you can simply say it. You cannot take 10 to some power to get negative 5, so it's undefined. Okay, why don't you take a minute, try filling these in, pause the video, and then come back and we can talk about this. Okay, so if you're having difficulty with any of these, you can always put it in exponent form. For instance, for 1, this would be a to what exponent would give you 1, and what it gives us 1 is 0. For 2, a to what power would give you a to the first will give you a. 3, a to what power gives us a to the x. Let's go ahead and look at this one explicitly. A to what exponent will give you a to the x, and you would have to fill in x to get that blank. 4, probably the most challenging. This, think of it as exponent form. We have a base to an exponent equals a value. So let's put that into logarithm form. So hopefully you're starting to see, if you're in exponent form, you are looking for a particular variable or value. Helps to put it into logarithm form, and vice versa. If you're in logarithm form, you're looking for a value, it helps to put it into mentally or physically by writing it down into exponent form. So here we're going to take this exponent term, even though it has a logarithmic expression in it, the setup of this equation is an exponent form. So a to an exponent equals a value. So now we're going to take that and put a logarithm, log to the base, which is a of the value, which now is the argument within the logarithm, equals the exponent. Well, that whole exponent is log base a of x. And then we say, well, what would we have to insert into the blank in order to make that equation equivalent on both sides? And you would have to insert x. So what this says, and we'll see this come up not too often, but what this says is if we have a base of a with an exponent that's a logarithm, provided that these bases are the same, then the whole expression is equal to the argument of the logarithm. So for 5, here we have a logarithm set equal to each other, then we can think of it as the logs canceling out, and x equals a. We can go through some algebraic gymnastics, I suppose, to search through that and make sure, but I think it's quite intuitive and obvious that the arguments would have to be equal if the bases are equal, very similar to 1-to-1. Okay, now we're looking at moving into logarithms with e. So our natural base of e, just like we had yesterday, but what does that look like in exponential? Excuse me, not in exponential functions, but logarithmic functions. And that looks like this. If we have a base of e, since e is very commonly occurring within exponential and logarithmic phenomena, we are going to create special notation where it looks like an L, an N, and then an X, and the way that we say that is natural log of X, which seems a little off given the fact that the L is first and not the N. I think there was a couple reasons for that. One, a lot of French mathematicians work on logarithms, and that could have been the order in which you say natural log. Could be the opposite in French. The other reason I would suspect is that since it's a logarithm, we just prefer that the L be first. But in any case, please do not use the term ln of x. Please say natural log of x. And whenever you see the natural log x, this is what you want to think in your head, log base e of x, because if we're going to need to solve for this, for instance, for the argument, we're going to write it in exponent form, or think of it in exponent form as far as e to the whatever number equals x. So whenever you see this, make sure you think this, but this is how we write it. One, for simplification of notation, or that's the main reason, because we're going to use it quite a bit. Okay, now getting into graphing logarithmic functions. So logarithmic functions we're inserting, or we're inversing the x and y, so it's hopefully obvious that logarithms, if it's not, it's fine. We're going to look more at this as we move forward, but logarithms are inverse functions of exponents. So for instance, if I have y equals a to the x, and then I put that into logarithm form, which would be log base a of y equals x, that would be an exponential equation. If I interchange the x and y, we see that we have log base a of x equals y, and that would give us our logarithmic function. Why do I say all that? Well, it's easy in an exponential function to pick the inputs, because I need to do, just like we did yesterday, 2 to the negative 2, 2 to the negative 1, 2 to the 0, and so on. It's easier to find that value, rather than trying to find a value and then the input or the exponent as a whole number that would give you that. So given that, instead of selecting the inputs for a logarithmic function, we're going to select the outputs. And it's going to be the exact same calculations as we did with the exponential function. So if we select negative 2 and insert it into the output, that'd be 2 to the negative 2 equals x, and we know that equals a fourth, but now that's our input. So log base 2 of 1/4 equals negative 2. This would be 1/2. This would be 1. Log base 2 of 1 equals 0, as we know. 2 to the first equals 2, and 2 to the second equals 4. I'm going to go ahead and graph those. So we have 1/4 negative 2, it's about right there. 1/2 negative 1 is right there. Get rid of that. So Okay, now 1, 0, 2, 1, and 4, 2. And if we look, that gives us our logarithmic function. And what you can do is, if you turn that, look at it in terms of the y-axis being the y-axis and the x being the x, we'd have an exponential function. Note, if you just turned it, you're going to get whacked out axes relative to positive for x and positive for y. You have to do a kind of like a flipping as well, but that shows the behavior is the same. And as an exponential, except about the x-axis instead of the y, we now have a vertical asymptote because our input has to be positive, because you can't have 2 to some exponent to give us a negative number. So now we see, let's go ahead and fill this in. Our domain is 0 to infinity. Our range is all y values, since that is the exponent. Our x-intercept is now 1, 0. Y-intercept is none. This is increasing. We don't need to write what interval it's for the whole interval. I made a mistake on that yesterday. I think we survived that okay. Horizontal asymptote is none, and then vertical asymptote we have x equals 0. So now this gives credence to why yesterday we had all this information. We see it's the kind of the reversing of the domain and range. Y-intercept goes x-intercept. We're still increasing because it's logarithmic growth. And then our vertical asymptote, we have a vertical asymptote rather than a horizontal. Okay, so now let's go ahead and look at if we're going to do a transformation on this. We have a +1 on the inside and a -2. So instead of having, now note the base is also e, since it says natural log. But remember the base, whether the base just like an exponential, if it's e or 2, you're still going to have the overall general behavior, right? So we're sketching the graph as it indicates. So that means we need the key point, which now is going to be 1, 0 rather than 0, 1. An asymptote, and then whether it's logarithmic growth or logarithmic decay. So first off, we're going to take our key point of 1, 0. We're going to translate it 1 to the left and then down 2. So our key point is going to be at 0, -2. Then we got to think of our asymptote. If our asymptote's right here, we're moving it 1 left. If we move it down 2, a vertical line moved down 2 doesn't change at all. But if we move it left 1, that would put us at -1. So we have an x of -1 for our vertical line. And then we go ahead and sketch. It's still logarithmic growth. That x-intercept may not be exactly right, but we'll see. We can do calculations on that. So now you just look at the graph. Domains is now -1 to infinity. Note with parentheses, because that's a vertical asymptote, never touches it. Range is still -infinity to infinity. You shift it down or up when it was original range of -infinity to infinity, that remains the same. X-intercept, we don't know exactly, so we can solve for that. Let's see what happens. So if we plug 0 in for each of x, and then natural log, I like writing it with a cursive L, x plus 1, just doesn't look like a 1 then. We look at that and we go, okay, well, how can we solve that? Well, as I explained before, if we're in logarithmic form and we want to solve for a variable, and it's not solved for the variable, then we want to put it into exponent form. And remember the importance of natural log, how we verbalize it, but remember what's important about this is we think of this as log base e. Because if you think of it as log base e, then this is much easier to turn into exponent form. So first off, we need to get it into a simplified form where it's just a logarithm set equal to a number. So we had to add over the 2. And now we can think of it as a logarithmic equation that we're turning into an exponential. E to this power, I'm literally going to write it out, e squared equals our argument of the logarithm. The argument of the logarithm is x plus 1. So again, e squared, I literally write it, e to the second power equals the logarithm argument, x plus 1. Subtract over, x equals e squared minus 1, and there's our x-intercept, so we can write as a coordinate. I'm going to write over here as a Marietta room, e squared minus 1. We don't have to particularly simplify that. E squared would be somewhere in the 6 region, right? 6, 7 region. Minus 1 gives us more in the 5, 6 region. So if you look what I have here, this is relatively accurate in terms of the graphing of it. And we also have a y-intercept. A y-intercept we simply get by plugging in 0 in for x. Let's see what happens. So if we plug in 0 for x, I'm going to do it over here. Sorry, I'm running out of room. Equals natural log of 0 plus 1, which would just be 1 minus 2. It also looks like we have it right here at, we know for certain it's 0, negative 2, because that was from our transformation, our two translations, but we can check to see if the algebra works out as well, as I'm doing. So when I plug in 0 in for here, I have natural log of 1. E to what power gives us 1? We know that equals 0. So that whole term goes to 0. So we have 0 minus 2, which just equals 2, negative 2. So our y-intercept is 0, negative 2. Decreasing, or no, I'm sorry, increasing. When would it be decreasing? If we had a negative out here, that means you flip the outputs, a reflection about the x-axis. But we don't have that here. And then, just to give you a heads up, the graph would kind of go something like that, where think of instead of going up and then kind of flattening out, we're going down and then flattening out. So that's what a logarithmic decay looks like. Horizontal asymptote, we have none, and then vertical asymptote, we have x equals negative 1.